Okay, welcome to the lesson on comparing linear, exponential, and quadratic functions. What we are doing in this lesson is we are attempting, without our TI Inspire calculator, to determine whether a set of points, the mathematical model for a set of points should be linear, exponential, or quadratic. And so I'll jump ahead and just show you the three examples. And so the idea is, without your TIs, we're going to be looking at tables of values, which of course are just sets of points, and we are going to be determining, using a method I'll show you in a couple of minutes time, whether or not an exponential function, a linear function, or a quadratic function fits them best, and then we're going to go ahead and find those equations. Okay, so a quick review of some of the characteristics of our functions. This, of course, a line. It is a linear function, and the form that it takes is mx plus b. M is, of course, our slope, and b is, of course, our y-intercept. And so those are the two things we would have to find in order to find the equation of a line. Exponential functions are, of course, asymptotic, so they approach, get infinitely close to the x-axis but never touch. And then as the value of x increases, in this case, the value of y grows very quickly. And so we have x in our exponent, we have our base, which is denoted b, and of course we have the coefficient of the base, which is denoted a. And the last of the functions that we are going to be using to try and fit to our data, if appropriate, is a quadratic function. The one that you see here has actually got its vertex not at the origin. What we'll be focusing on today is functions in the form of ax squared, and so we don't need to worry about a vertex that moves the parabola left, right, up, or down. So we're just focusing on parabolas that open up or down at the origin. Okay, and then just a quick note, since these are algebraic functions, the concepts of domain and range apply to them, all of them, just as they do to all functions. Okay, so what we're going to do is, in order to determine which of the three functions we want to fit, if any, to our data sets, is we're going to be using successive differences in our table of values. So I'm going to show you what I mean by that. You'll notice that the x values for each of the three examples are essentially the same. The exception is example 3, where we've just added in an additional point, but all of the x values are the same. They've been substituted into an equation to produce the corresponding y values, or rather, we've collected this data, we've got the set of points, and we're trying to figure out which mathematical model would fit it best. And so we're trying to figure out, does it follow a linear pattern, an exponential pattern, or a quadratic pattern? Okay, and so the way you can determine that using a table of values is to find the differences between a term and the term that came before it. Okay, and so if I take 5 and I subtract 2, then the difference between those two terms is 3. I'm going to repeat that process. If I take 8 and I subtract 5, you can see that we obtain the same difference. And one more time, if I take 11 and subtract 8, we once again get the same value. What this tells us is that the function that this data fits is in fact linear. And what you'll notice in your note that is detailed below. So if the differences of successive y values are equal, then that tells you that the function is linear. And what it also in fact tells us is that if each subsequent term, and you'll notice these are in order, if each subsequent term in this case increases by 3, then that has in fact given us our slope, and all we would need to do is find the y-intercept to find our equation. Okay, we're going to repeat the same process with example 2 and example 3, and I'll show you a couple of differences here. So once again, 0.5 minus 0.25. This time I'm going to get a difference of 0.25. Repeat the process. 1 minus a half is going to give me 0.5. One more time, 2 minus 1 is going to give me 1. And in this particular case, you can see that the first differences are in fact different. They do not produce the same numerical value. So what we do in this case is we repeat that process one more time. 1 minus a half, 0.5, 0.5 minus 0.25, and once again we see that the two differences are not the same. So what this does is this tells us that the function is neither linear nor quadratic. And what we're going to do now is test for the third option, which is using ratios. So what we're going to do now is we're going to use division. Same idea, we're going to pick a term and divide by the previous term. So I'm going to have 0.5 and I'm going to divide by 0.25, and in this case the answer is 2. 1, and I'm going to divide by the previous term, which is 0.5, and that once again produces 2. 2 divided by the previous term, which is 1, and that will once again produce 2. And what we have here is a common ratio. So when we divide, all three of the answers produced are the same, and so that tells us that this function is in fact exponential because the ratios of the successive y values are all equal. Okay, so one more time for example 3, I'm going to go back to the subtracting process and we'll see. So we have 0.5 minus 2 is going to give us minus 1.5. We have 0 minus 1 half is going to give us minus 1 half, or minus 0.5. 0.5 minus 0 is going to give us 0.5. 2 minus 0.5, 1.5. And what you can see very clearly is that the answers in this case, the first differences are not the same. So we'll repeat the process. 1.5 minus 0.5 is of course 1. 0.5 minus negative 0.5 ends up being added, and that of course produces 1. Minus 0.5 minus 1.5 of course becomes plus 1.5, and once again we end up with 1. Our second differences are all the same, and that tells us that this function is quadratic. Quadratic function, second differences of successive y values are equal. And so what remains to do now is to write equations for each of these. And so we have one linear, one exponential, and one quadratic. And so our linear function is in the form y equals mx plus b. So let's start there. Example 1 was linear. We already have our slope. The y-intercept is of course b, and the y-intercept occurs when x is 0. And so fortunately for us, on our table of values, we have the point x equals 0, y equals 5, and that tells us that the y-intercept is in fact 5. So I'm going to come down here and write my equation for my line. Y is equal to 3x plus 5, and that is the equation of the function that fits the table of values in example 1. Example 2, now what we're dealing with in this particular case is exponential growth in this case, and so we have an exponential function, and so I'm going to move back down over here. There's some details on how you're going to find this. So what we're looking for is an equation in the form y equals a times b to the power of x. B is, as I mentioned earlier in the video, b is our base and a is the coefficient. And so what you should hopefully remember and realize is that the base of 2 has been revealed by the common ratio. And so the common ratio is in fact b, and b in the context of exponential is of course the base. In the context of linear is the y-intercept, but in the context of a an exponential function, we have a times b to the power of x. What we've determined already is that b in this case is 2, and in order to determine what the value of a is, we can, as is often the case, and we could have in fact done with the first one, is we can select a point from the table of values and substitute it into that equation. Again, for the purposes of simplicity, it's easiest to pick the point 0.5, or to pick the point, in this case x equals 1, y equals 1, because that gives us a nice, easy equation to solve when we're looking for a. So in this case, I'm going to pick the point 1, 1. Could in fact pick the point 0.5 as well. Either of those will work. So I'm going to substitute in the point 1, 1. That means y is 1 if x is 1. 2 to the power of 1 is, of course, 2. I can divide both sides by 2, and I am able to conclude that a is equal to 1/2. And now I can write my final equation as 1/2 times 2 to the power of x. And that gives me my exponential function. And last but not least, for example 3, we are looking to find a quadratic function. As I mentioned before, we're only interested in quadratic functions in the form ax squared. We're not going to worry about bx plus c. And so if we come back up here, and what you can see is the differences for us here simply confirm that this is going to be quadratic. And what we're going to do now is we're going to pick a point, not 0, 0, because of course if we substitute in 0 and 0 for the x and the y, that's just going to cause what's known as an equality, where both of the sides will equal 0, and that's not going to help us to find the value of a. So I'm going to pick one of the other points. Any of the other points will do. I'm going to pick the point 2, 2. Could have, of course, picked the point 1, 0.5, or one of the negatives, but of course that does complicate things. Come down here, substitute those values in. So y is 2 when x is 2. That gives us a times 2 squared is, of course, 4. And divide both sides by 4. And once again, I have a equals 1/2. And so my equation, 1/2 x squared. And we have now successfully found equations for each of our 3 examples. In the event that the first and second differences revealed that it was not linear and it was not quadratic, and then we looked for common differences and it was not exponential, then of course they are none of the above, and in that case we would be working on the assumption that it either fits a function that we're not familiar with, or it does not fit a function at all. Okay, so at this point you should make sure you copy this note down and then turn your attention to the assignment, all of which comes from the new blue textbook, and get to work on those.